While you were away, I changed our mind for us. We're actually going to do the LSAs after we do these labs because I want you to see them on the live equipment and not just on the board. Nothing wrong with looking at them there, but we'll look at them on the live equipment as well, and we'll discuss a couple of different LSA types. And they will definitely ring truer with you when you've seen the configuration of this particular network, because this is actually going to be a couple of labs in one. We're going to configure a hub and spoke OSPF network. Then we're going to add some loopbacks, and then we're going to add our Ethernet segment back that we were troubleshooting adjacencies on in earlier videos. I've got a diagram for you in a moment, but you might want to write these addresses down. Over the frame network, that's our NBMA network. We're going to use the 172.12.123.0/24 address space. Over the Ethernet, 172.23.23.0/24. And please notice that we do not have the world's most realistic network when it comes to the NBMA network, but you could see something like this. And on an exam, anytime from the CCNA to the CCIE lab, anytime you see different interfaces mixed in over the cloud, over your serial interfaces, they're testing your knowledge of whether you know how these interfaces actually work. And you're going to see how they work with OSPF, and I think we're going to have to do a little bit of troubleshooting and debugging on one of those networks. If you can spot the one ahead of time, fantastic. Router 1 is using serial 0, the physical interface, one we've been using for most of our labs. Router 2 is using a multi-point sub-interface, serial 0.123, and then router 3 is using serial 0.31, a point-to-point sub-interface. Each router has a loopback with its own number for each octet, and each loopback has a host mask. So that's 255 for all 4 octets. And you can see what we're going to build here. We've got area 0, our backbone area, is our NBMA network. So if we don't get that working, we don't have to worry about the other areas, but we'll get it up and running. Area 23 is going to be configured over our Ethernet segment, and each loopback is in its own numbered area, numbered after the router, of course, 1, 2, and 3. We will be taking it one piece at a time, and we're going to get that NBMA network built first. This is going to be one of the most detailed labs you see. I'm not trying to scare you. It's not tricky, but there are details with an NBMA network that you just don't have with other ones. Because let's face it, I think we configured the Ethernet network 2 or 3 times when we're doing the adjacency labs. You put the network command on, and if everything else is fine, that's it. But with the NBMA network, we definitely have more details. Now we're going to chat about OSPF areas just a bit before we configure area 0 and get started. Now area 0, that's our backbone area of OSPF. And in an exam this might happen, but of course in a production network it is going to happen, where you're the one looking at the diagram and saying, okay, here's what I've come up with. Is this legal? Is this going to work? Well, the deal is that every non-backbone area must contain at least one router, not entirely contain it, but just have one interface from that router that also has an interface in area 0. This topology meets that requirement. Going a little bit beyond the scope of the NA, I usually say that has a physical or logical interface in area 0, because if we just can't get a regular interface in area 0, we can build a virtual link to area 0. That's for future studies, unfortunately, because I like building those, but we have enough to do here, as you see. Now, about the OSPF areas, let's chat about those for just a minute. As you go through OSPF, and you've already had some here, but you haven't gotten to these different area types. And we can configure stub areas, and we can configure total stub areas, and we can configure not so stub areas. I'm not kidding, that's actually what it's called. And we don't do any of those in the NA, but as you progress through your studies, and even as you go through these, you just think at some point, hey, why don't we just chuck everything in one big area 0 and just be done with it? Why are we going to all these troubles, and we have the different LSAs, and we have different stuff we have to watch out for? Why don't we just chuck them all in one huge area? Well, that's a great question. And there are several excellent reasons why we use areas. And it's where I usually say as a quick answer, well, it helps limit the impact of network changes. And I've seen, authors do that, and other people say, oh, well, it just limits the impact of any problems you have. Well, that sounds fantastic, Professor, but what exactly does it mean? I'm glad you asked. If we just leave all of our routers in one area, the databases are going to get pretty darn large. And certainly that's a relative term. You know, our databases with a 3-router network are not going to be huge, but we don't run OSPF over very many 3-router networks. We run them over enterprise networks, which can have a lot of routers. And then all of a sudden you've just got huge databases on every router if we just had them all in one area. So you might think, well, you know, so what's the harm there? Well, it's kind of, I wouldn't say a trickle-down effect, but it's kind of more of a domino effect. Because any network change in that scenario means that every single router in your ginormous area 0 has to run the SPF algorithm. Now, it might not sound like much, you know, but it's generally unnecessary and it's a hit to the CPU. We're always trying to reduce that a bit. And of course, the database is sucking up memory because it's just getting bigger and bigger and bigger. And the bigger the database gets, the slightly longer it takes to run the algorithm. And of course, that's more of a hit to the CPU because it's a more complex operation. So the helpfulness of areas does become clear there because it's just this little domino effect. As it gets bigger and bigger, it takes up more space in our memory. It takes the SPF algorithm longer to come up with the routes that we need, and it has to work harder, basically. And again, in a lot of places, including some that we'll see in this part of the course, it's unnecessary. So the areas really are helpful. Now in turn, our OSPF areas define OSPF router types. Now these types are not all mutually exclusive. A router can be more than one, and you need to be ready to identify these on the exam. An internal router is one with all the interfaces in one non-backbone area. A backbone router is one with all interfaces in the backbone area. The area border router, this is a router with at least one interface in area 0 and at least one interface in another area. So if we go back to our current network, or the one we're about to build, we have how many ABRs here? We have 3 because all 3 of these routers are bordering area 0 and another router. And I'll show you a command that will actually tell you, you know, this router is an area border router. But you should be ready to spot them on the CCNA exam. This is beyond the scope of the NA, this one I'm giving you right here, but I want you to know about it because if you're working with OSPF or you're going for a job interview, you're going to look a little silly, frankly, if you don't know what an ASBR is, but you know what an ABR is. It's an Autonomous System Border Router, an ASBR. Now, the term autonomous system makes you think of EIGRP, but it doesn't have anything to do with that. This is a router that is performing route redistribution, redistributing routes into OSPF. Now, route redistribution isn't on your CCNA exam, but as a bonus, what I'm going to do is do a little quick redistribution at the end of our lab here, and you can see how to verify that a router is acting as an ASBR. That's more for job interviews and your knowledge. But if you know what these 3 OSPF router types are, internal, backbone, and ABR, you should know what an ASBR is. Now, let us dive into the lab work, and we're going to dive into this right now. The OSPF configuration, I say on the board, you'll see that it's very straightforward. You've already seen that actually with our adjacency troubleshooting. But a hub and spoke OSPF deployment has to take a couple of factors into account. The first is that the spoke routers must be prevented from ever becoming the DR or the BDR. Ever. We don't even want them to take part in the election. Because the thing is with a hub and spoke, what's going on with that hub, right? Spoke to spoke communication has to go through the hub. Well, we need our hub to be able to send hello packets to all the spokes. If a spoke router becomes the DR, it can't send multicast to another spoke because they would have to go through the hub. And what's our #1 default rule there? Routers don't forward broadcasts and multicasts. They receive them, they accept them, they generate them, but they won't forward them. So we have to fix this election to the point where not only must router 1 become the DR, we don't want any of our spokes to become the BDR, because even if router 1 goes down, we don't want any of the spoke routers taking its place as the designated router while it's down. That's how serious the situation is here. Now, the default priority of an OSPF-enabled interface is 1. the interface with the highest priority becomes the DR, and the interface with the second highest priority becomes the BDR. Remember the pri for priority we saw in show IP OSPF neighbor? That pri is the interface priority of that neighboring interface. So it would be tempting just to say, well, what we'll do is set the priority on the hub to a number higher than 1, and it'll win the election. That's true, and you'd be fine unless that hub router goes down. Because it's not just enough for router 1 to win. And I know I said this before, but I got to reiterate it. It's not enough for router 1 to win. Routers 2 and 3 must not even participate in the election. So we're not going to go to the hub and change the OSPF priority to a value higher than 1. We're going to go to the spokes and set the priority to 0. So we're going to disable them from even participating in the election. We're going to do that at the beginning of the very next video because we're at 11 minutes now. I don't like to go too much longer on one video, and this one's going to take a little while. So I'll see you on the next vid, and at the very beginning of it, we'll hit the lab work.